Good afternoon, everybody. Welcome to the Atto Fridays. Our speaker today is Dr. Christian Ott. He is a staff scientist and group leader at the Max-Planck-Institute for Nuclear Physics in Heidelberg, Germany, in the division Quantum Dynamics and Control, and he's working with Professor Thomas Pfeiffer. Christian received his doctoral degree in 2012 from Heidelberg University on attosecond interferometric techniques and strong field control of two-electron dynamics. During his 2 years postdoc with Professor Stephen Leon and Daniel Neumark at the University of California, Berkeley, USA, he studied strongly correlated materials by means of attosecond transient absorption spectroscopy, sponsored by a Feldolinen postdoctoral fellowship of the Alexander von Humboldt Foundation. Christian is leading research efforts which include the fundamentals of absorption spectroscopy, resonant light-matter interaction, and few electron dynamics in small atoms and molecules, and their ultra-fast control, employing both lab-based lasers and high harmonic generation in large facility FEL ultra-fast light sources. And today we are going to hear about XUV light. And his talk is on All-XUV-optical nonlinear light-matter interaction with free-electron lasers. So welcome to the Atto Fridays, everybody, and welcome to Dr. Ott. If you're ready to start, we are ready to hear you.
I am ready to start. Thank you, Carla, very much for this very nice introduction. And of course, also thank you for the invitation to be part also of this wonderful series. It's really a nice organization of keeping the community together. And yes, in this talk, I hope I can give you an overview of the research that we do with nonlinear light-matter interaction with intense XUV fields that we use at free electron lasers. And you see basically on the top a schematic view of the setup already. So in principle, it's very simple. Take an intense beam from an FEL, direct it through an atom, it gets absorbed, and we look at the transmitted light with a grating spectrometer. And from the spectra that we then obtain, we can actually extract huge information. And here in this nice picture here, in the photographic image, you see also what's going on inside the target, the cells. So you see nice, because we have dense materials, plasma recombinations and plumes and this. So let me start right out. So the XUV and X-ray wavelength range, I just want to introduce you, so very basic. What's the deal about this? It's in principle, it's ionizing radiation, of course. So we live kind of in the continuum where we have an atom that is pictorially sitting here. When we excite this or stimulate this by a high intensity or in a high energy photon, as you have seen in this small animation, there's an inner shell excitation or also ionization going on. And then subsequently, we have the Auger-Meitner decay or also auto-ionization relaxation. So that is all electronic reconfigurations that are happening. And this is happening on very, very short timescales. So typically on a few femtosecond and attosecond timescale until the electrons leave and, so to say, the coherence is carried away. And in our research, the scientific goal that we have is to look at these multi-electron dynamics that are site-specific, that are happening on an ultra-fast timescale. And we want to not only look at this, we want to understand this and also deliberately control this. And the control is done through the interaction with really intense radiation fields, so where we enter the nonlinear regime. So physics with XUV and X-ray light goes way back. Of course, X-rays have been discovered no more than a century ago, but especially in the late or in the 1980s and in these decades, the XUV and X-ray spectral range were realized as really precision tool for to address inner shell and core shell atom-specific electronic transitions that are really a marker for each atom. And here Kai Siegban is a key player, developing high-resolution spectroscopy, measuring photoelectrons, and basically with synchrotron radiation to employ the XUV and X-ray light as a high-precision tool. And it's really a site-specific local probe of the molecular structure and the dynamics. And here's like an overview of the different wavelength ranges, and you see that the X-rays, they cover a lot of different edges of the atoms. On my next slide, I have here a list of the inner shell K and L edges of different atoms, like the carbon, nitrogen, oxygen is located at around 300, 400, and 500 electron volts, and also further up are the L edges of different transition metals. And one dream in the community is to have really a microscope to see what happens also on ultra-fast time scale. And this is in the attosecond community. This is a famous example of this charge migration dynamics. So you ionize an inner shell electron, or you excite an inner valence system, and then due to electron correlation, the charges are migrating. It's basically you form a wave packet that is induced due to electron correlation, and this unfolds on ultra-fast timescales. And there's many different methods to observe this. Of course, in the attosecond community, this has been observed already with different techniques. It would be really nice to see locally what happens at different sites in the molecule by means of going to the carbon, nitrogen, oxygen edges and to directly look at that. So that is one key driver. And we have, of course, modern sources of XUV and X-ray light. So this is on the one hand, these large-scale facility sources, free electron lasers that basically generate the light by accelerating electron bunches to relativistic speeds over really huge length scales. So here you see aerial collage of aerial photographs of different facilities. And on the other hand, of course, this is at the very heart of attosecond community. We have strong laser sources and strong laser sources in the lab available that we can direct into dense gas media and then exploit the cycle, the waveform of these laser pulses to generate attosecond pulses that are sitting in the XUV and with some long wavelength drivers even in the X-ray domain. And basically, from my PhD work, I'm coming from this side, and even while we still continue lots of work in this area of lab-based research of steering and controlling electron dynamics in small atomic systems, we also looked at transferring some of these concepts to free electron lasers. And this is what I would like to talk to you about. And in what is in the content of this talk, I'm mainly using free electron laser that is here depicted on the top left. That is the Flash free electron laser facility, the first XUV free electron laser that came online not quite some time ago. That is in Hamburg, Germany. And these are, as I just introduced, totally different scales. So the scale, of course, for these accelerators is in the kilometer range. So really huge, while the high harmonics in the lab are scaling in the meter range. So that is still inside one single building. And so you have, of course, typical different specifications, even though nowadays there's quite some merge between the two fields. And actually lots of people scientists in the community gather experience with both sources. And so each community that have been maybe a little bit more separate in the past are really benefiting from each other tremendously. So typically you have the shorter pulse duration, of course, with lab-based attosecond pulses, you can nicely synchronize them. And on the other hand, with the free electron lasers, you really go to the extreme X-ray range and also the high pulse energies. And the pulse durations, so if you sacrifice a little on pulse energy, you also go in the few femtosecond and even attosecond range. So, and light fields are in general very compelling to use because you have a huge control possibility. You can control the timing, the photon energy, the intensity, polarization, and use these light fields and to control basically the interaction, the nonlinear interaction with matter. So this is what this is about. And the tool that we use is absorption spectroscopy. And just very simple, what is absorption spectroscopy, how we implement it? It's basically as simple as this sketch that you have a broadband light source that you emit through a target. It is absorbing due to resonant electronic transitions. And this light then is missing in the transmitted spectrum, such that when you disperse the transmitted spectrum here linearly in the linear interaction regime, you see, of course, a dip in the transmission spectra. So this is very much related to the extinction coefficient or the complex refractive index, the absorption coefficient. And just as a little history background, so already in the early 19th century, Fraunhofer observed different lines in the solar spectrum. So when you have the light source at the sun and in the solar atmosphere, the absorption, you see here all these resonances as a dip in these spectra. And coming from Heidelberg, it's always nice to mention Kirchhoff and Bunsen that in the 1860s, they really put this on a systematic scientific footing, basically starting the spectral analysis that one could identify different elements in these spectra, and which is basically the foundation or one of the foundations of our modern view of quantum physics. And our target of interest, so we are coming from very small targets where we have the approach to try to understand as much as possible from them. And there the helium atom has been playing a key role in our research. And there I show you here some basically data and photographic images of early absorption spectroscopy in helium with white light from synchrotron generated by bending magnets, basically shooting or directing a broadband light source through the helium atom. And you see already here resonance is appearing in the 20 nanometer range. So that's around 60 electron volts. And you see these line shapes here are asymmetric, and this asymmetry stems from a correlated transition with 2 electrons being excited with 1 photon at once. So I told you I come from lab-based research. So here's a typical experimental setup that we then used in the lab. So we have a high harmonic generation cell, direct intense laser pulses through the target cell. And with a split and delay unit, we basically separate these laser pulses in time and in space and focus them then on the absorption target cell in the interaction region. And here you see actually a photographic image, how it looks like in the lab when you focus intense laser pulses through these high density gas cells, where the gas is coming from the bottom and there's an opening to the left and the right. And the key importance of this setup is that we have many control knobs. So we can control the intensity of the infrared disturbing or controlling laser by means of an iris aperture. We can control the time delay by means of a piezo-controlled mirror. And we span then, after transmission through the target, the XUV light on a broadband detector. We spectroscopically analyze this target with a grating spectrometer. So we have a third dimension opening up. That's, of course, the energy resolution. So we get at the same time a high energy resolution, a time delay control, and an intensity control. And then we can have multi-dimensional data sets. And a few basics. So how is this interaction possible and how is it not contradicting Fourier principles? Let me introduce this to you in a very simple way. So take an attosecond pulse and you shine it through a dense medium where typically the atoms are still far apart, so that it's still isolated systems. So on atomic scales, the distances to neighboring atoms are still huge. And then if you have a non-resonant interaction, for example, in the XUV, just an ionization, into the continuum, this attosecond pulse would be just attenuated, and you see in the transmitted spectrum, the width of the pulse stays the same, it's just attenuated. And this is following, of course, in the linear regime, Beer-Lambert's law of attenuation. And the twist now that we do is what happens if we use intense pulses. And in the lab, we were mimicking, or we were realizing these intense pulses with an added infrared laser pulse that's coming through. So how can we now control this? So in the attosecond community, photoelectrons, you all know you can streak them, you can create sidebands in harmonic spectra. So that's famous streaking and rabbit experiments to be sensitive to attosecond delays. That's of course then when the infrared laser pulse is interacting with the already ionized electron. But in the absorption spectroscopy, what you interact with is with the active medium, so to say, that the XUV pulse has activated. So in this interactive medium, how can you now think of or measure these electronic resonant transitions? So that is basically the keys that you need to know for that. So in linear absorption spectroscopy, so now let's first forget about this infrared laser. And if this is now helium doubly excited state, and you hit the resonance for this 2-electron transition, you see that in the transmitted spectrum, the asymmetric line shape is just encoded as an attenuation in this transmitted spectrum. So how can you think of that in the time domain? Well, that's basically the response function, or the response function mechanism. It's the dipole tail. There's a dipole response that this XUV pulse has generated after transmission through the medium, and this medium is active during the whole lifetime of this 2-electron excited state. And this has typically a lifetime here on the order of 20 femtoseconds. So with 20 femtosecond decay, there's an exponential dipole that is attenuated then after this pulse. And in forward direction, these two pulses, so to say, so the initiating attosecond pulse and this dipole decay, they interfere in forward direction and are both detected on our spectrometer. And because the spectrometer is time integrating, we are integrating over this whole time scale here. So here is where Fourier principles are not broken. So you have here a sharp spectroscopic resonance in the transmitted spectrum. And this is really the key to understand this. And this is what I write down here is basically another implementation or illustration of Beer-Lambert's law. So what we measure is the optical density. The optical density is the absorption. It's like in Beer-Lambert's law, dividing the transmitted spectrum. So here the solid curve through the incoming spectrum here on the left, or what's here on the right as the dashed curve. And after division by that, and then taking the logarithm, you get what is inside this exponent in Beer-Lambert's law. And this optical density, that is proportional to the imaginary part of your refractive index. So that's really easy Maxwell propagation of radiation field in this light-matter interaction, classical radiation fields propagating through this dense medium, the imaginary part of the refractive index, which is in the dilute medium proportional also to your susceptibility. And this in turn is directly proportional to your dipole response. And that is the key microscopic quantity that you can access here. So take home from here is that inside this medium with the strong field or with the weak field now, we still forget about the strong field, we initiate the dipole response. And the time-dependent dipole response is written here in this quantity. We take the Fourier transform of this. This is the dipole spectrum, or the complex valued dipole spectrum. And the division of that by the incoming electric field spectrum and the imaginary part, this is what makes, in the end, the absorption. And the twist, the nonlinear twist that now comes is the addition of the infrared field. Of course, when the infrared field then interacts with these excited and active media, it can, it has not mainly an influence now for this here on the ionized electrons, but it has an influence on the excited states of these systems. You can couple the different states, and what you could do here is adding this infrared field might just change the dipole response in a very minute or a very small way, shifting the phase, for instance, of this dipole. And by just simply shifting this phase of this dipole response, it has a huge effect on what can be measured in the spectrum, because by shifting the phase of this oscillation, you basically tune this interference. And it turns out that by doing that, you have a huge control, a decisive control on the line shape. And that is how we started this whole research, by observing that we can do this in the experiment in the lab. And that's what I'm showing you here. So this is where we controlled the spectral line shapes, observing naturally asymmetric phonoresonances in helium. So this asymmetry comes about in this cartoon on the left, bottom left. You have 2 electrons in the ground state in helium. When you come in with 60 electron volt photons, broadband spectra, you can go directly into the continuum, or you can go through this 2 electron excited state. And this lives for about 20 femtosecond, or in this case of these resonances, even longer, like 80 to 100 femtoseconds. And this decay here then also leads to this continuum, and this is a quantum interference effect, which from the quantum interference leads to these asymmetric resonances that are characterized by a cross-section. So this is still all in the linear regime, where the concept of cross-section is well defined. And it has this famous Q asymmetry parameter that is defined by Fano. And this, by adding now a separate laser electric field, as I showed you in the illustration before, we dress this dipole response. We, for instance, induce an energy shift that is taking place only over a short time. And these energy shifts are connected to what you all know that you can do with strongly coupled resonances. So you have Stark shifts and Rabi, like other strong field effects. And this energy shift integrated over a short time is encoded directly into a phase shift, which then leads to the mapping that can be found analytically of the asymmetry of this line shape to this phase shift. And in this whole formalism, we kind of neglect here that the dipole response of the continuum channel, that is what's illustrated here, is more or less instantaneous. So this here, we don't, the dipole response of the continuum is basically unchanged, and we most decisively control the dipole response of the bound state. All right, and this is now just some highlights that have been possible with that. So I don't want to go too much into that detail. So this is still kind of introduction, which is a little bit lengthy. Now I want to soon go to the free electron lasers now. But we could here resolve a 2 electron wave packet by identifying which of the 2 electron excited states that you can resolve here in energy, and couple as a function of the time delay. We see an ultra fast few femtosecond or even 1 femtosecond rippling that is reminiscent of this 2 electron wave packet that can be excited. And by increasing the intensity of this intense electric field, we can truncate this dipole response at a certain time, and therefore allow this, so by Fourier principles, allow this 2 electron absorption line to be born, to be built up in real time. So we can look at how the correlated 2 electron line shape is building up if we allow longer and longer the dipole response to be radiating, so to say. And it's actually a direct way. If we look at that, this dipole response, it's triggered by an isolated single attosecond pulse. And that's what's encoded in the absorption spectrum. So we can take this step back and actually Fourier transform the absorption spectrum to get really the real-time dipole response. And that is what is plotted here in this graph. This is not scanning any time delays. It's a single fixed time delay. The infrared pulse sits at a certain time after this exciting XUV pulse, but taking just the Fourier transform of the observed spectra, because we have used a single attosecond XUV pulse, we can extract the real-time dynamics directly from these line shapes. And that is kind of, I find this kind of cool that we get a real-time view into the laser-driven two electron dynamics that are now centered on a certain resonant state. All right, so now after this lab-based introduction, now the question we want to ask is, how do these atom-specific resonances look when we view them through the interaction with intense radiation fields that are exclusively now in the XUV part of the electromagnetic spectrum. So for the remainder, just forget about the intense infrared field. Just the dipole response exciting electric field will get strong. So what's happening there? So this is the experimental apparatus that we have installed. So this is now already some time ago. So this was an installation that was only running for a single beam time. So we brought basically this whole apparatus here at an open port beamline at Flash in Hamburg, where the FEL beam is coming from the right. It's impinging on this target cell, and basically lots of steering and vacuum chambers where we make sure that the beam is then directed in the end all the way downstream at the bottom on a grating that you see here in this zoom in view. This is a variable line space grating, reflective, and it's then dispersing the radiation, of course, with lots of attenuation and filters in front of that onto an XUV sensitive CCD camera. And Thomas, Lennart, and Mark are the key players that have basically designed this and constructed this beamline from scratch, and of course performed very successfully these experiments. And if you're interested more in this experiments and also what other experiments we have done, so if you're interested more in the setup, I wanted to say, you can look up this this write-up application here. So that's a schematic view of all the different chambers and the steering into, from the left now comes the FEL, all the way to the right to the spectrometer, and in the main target chamber we have the interaction, and then basically steering and routing. All right, so I started with an introduction on the helium atom. So this is the first experiment we did. We directed now intense XUV radiation through this helium atom, centered at 60 electron volts. We can excite them into this 2 electron excited state, which is here pictographically illustrated in the center. And this has this 20 femtosecond roughly lifetime of this excited state. But if this interaction, this radiation is now intense, there is the possibility that you can drive this transition up and down, and you have kind of direct level splittings. And this is actually, as a teaser, what we will see. And what can be observed in the lab is the FEL spectra. So this is not like a stable laser source. It is based on self-amplified spontaneous emission. That's why it's fluctuating from shot to shot. And the tricky part in the experiment is now to identify in the transmitted spectrum the reminiscence of the helium atom, where in parallel we measure also the incoming spectrum. And after averaging, well, first I can tell you that actually here at a certain energy position, there's always a dip, which is more pronounced if we average over all these spectra. So averaging the incoming spectrum gives you a Gaussian-like distribution. And in the transmitted spectrum, you see here an additional dip. And this is proportional to the density of helium atoms that we have here in place. So how is this now happening? Here's a summary of the parameters that we use for that. So we have basically 50 microjoule pulse energies that we put on target, focusing to 25 micrometers. So this gives us fluences on the order of 8 joules per square centimeter. So fluence is the integrated flux that is inside this intensity envelope. And you can think of these SASA spectra as intense spikes, where each single spike can get even more intense, reaching intensities of 10 to the 14 to 10 to the 15 watts per square centimeter. So that's the right range where we can see here nonlinear interaction. And while on average, the duration is relatively long, but you can think of this experiment as a bunch of micro experiments where each of these intense spikes now triggers this dipole response. And basically we see some average over all these effects. And this broadband spectrum we were directing on this Fano resonance in helium. And the conceptual idea now is that we also strongly couple these states, now a 2-electron transition from the ground state to the excited state. And due to the strong coupling, induce with the intense radiation fields energy shifts over a short time, where this time scale now is the time scale of each of these intensity spike, which it turns out is here on the order of 5 femtoseconds. This encodes a phase shift that is then encoded again in a different line shape. And show you directly the results that we get here. So we see this asymmetric Fano resonance. If we increase the XUV intensity, which is here the directly measured quantity, is the pulse energy that we put into these radiation fields. If we increase that, we see at different intensities, basically different asymmetric line shapes, where you see at the highest intensity, we see a more symmetric, attenuated, but also symmetric line shape that is in helium. And with a model, we could understand this basically based on the same principles that I introduced before with the lab-based laser control. So we modeled with 5 femtosecond Gaussian-shaped pulses that are centered at 60.1 electron volts. So that is mimicking one single of these SASA spikes. And if we increase the intensity also from the model, we see that the line shape asymmetry changes and it's getting more symmetric. And fitting these line shapes and invoking this analytic correspondence between the phase and the line shape asymmetry, we extract these different phase shifts that are happening then. And again, these phase shifts are due to a short time dressing of the excited state energy. And these phase shifts here are basically equivalent to the ones that we can extract directly from the simulation. And by taking the derivative of these phase shifts, basically taking the derivative with respect to time, we get again, of course, these energy shifts. So we are sensitive here to strong coupling induced XUV transitions where the energy shifts are on the order of 20, 10, 20 millieV. And this is to be noted, we don't see these energy shifts as a shift in energy here, but we see this due to this short pulse interaction in this interferometric line shape asymmetry change. And from the model, we could also look at the populations of these states. So one nice thing of this kind of regime that you get in, if you use here 10 to the 15 watts per square centimeter XUV pulses of 5 femtosecond duration, you actually manage to not only deplete the ground state here, which is shown with the black curve on the population, but also excite this 2-electron excited state. And for a decisive non-zero fraction of time, you have actually more population in this 2-electron excited state than in the ground state. So this demonstrates that you can use these intense electric fields to do quantum state population control of this here auto-ionizing 2-electron system. Where, of course, if you can now come with additional pulses, time synchronized, you could then go further with that. And we also looked at the impact of the SASA pulse duration on that this has. So Leonard looked at the data again, and actually we went again to the free electron laser with different settings, where here is basically the results that I've presented to you just now, where we see that with increasing pulse intensity, the asymmetry Q parameter changes and the amplitude goes down. And we repeat this measurement with a longer, on average, SASA pulse. So you see here, a longer pulse has fewer more and not so intense spikes, rather than with the short pulse, you have fewer and more intense spikes. And in this long pulse scenario, we were just seeing that the amplitude goes down. So this is basically ground state depletion and incoherent effect. But the Q parameter, the line shape asymmetry, stayed the same over the whole range. And this can be attributed to, this is from a simulation, a histogram of, for a rather short pulse with a 30 femtosecond envelope, you have more spikes that are reaching into this 10 to the 15 watts per square centimeter range. And you have less spikes with the longer pulse durations. You have more spikes that are only here in the 10 to the 13 to 10 to the 14 watts per square centimeter range, where you don't yet enter into this strong coupling regime. And we took this further, so this is relatively new now. We also looked at these line shapes and observed that they also broaden with more intense pulses. So this is basically the experimental observation, that you see a broadening with increasing the pulse energy from top to bottom and extracting the width of these resonances. We see a decisive broadening here. And from a model, we checked, can this broadening actually be due to an additional ionization of these two electron excited states? So we also plugged this into the model, and we put in different ionization cross-sections for these excited states. So comparing it to a system that mimics this. So these are on the right order of magnitude. And we see that indeed increasing this ionization broadens, in addition, the line shape, as you see here, with the line width increasing with increasing cross-section. But we see that also with zero cross-section, so switching off this additional decay channel, increasing the fluence or the XUV intensity already broadens the state. So that is actually already the strong coupling back to the ground state, and the ground state can also directly ionize. So you change kind of the balance in this, if you so wish, Fano interferometer of addressing this two electron state and going into the continuum, which gives us the broadening. So we can identify from this work that the strong coupling effect has the dominant contribution. So now let me move away from helium and show you some more results that we got there in time resolving atomic resonances in neon atom also. You see here, this flickering light is basically the 10 Hertz light source, where the FEL is now in a pump probe geometry. So also preparing for molecules that I'll show you later. It's transmitted here through the absorption gas cell. And this has been done back then at the Beamline 2 with the help of Helmut Zacharias and Sebastian Bohling from the University of Münster, which have this split and delay autocorrelator or split and delay unit that is basically with a reflecting the spatial beam at different positions and delaying them with respect to each other. We can realize pump and probe pulses in the XUV, directing them and overlapping them in our absorption target. And later downstream, we can select them with the precision slits. So that's all in the components of this complex setup that I showed you. There was many more vacuum chambers, so these slits are also part of that. And in our detector, with the spatial coordinate in the vertical, we can now resolve and look at the pump and probe pulse separately and disperse them on photon energy. And if you now time delay the probe pulse and measure the probe pulse measure this in the spectrometer, when the pump comes first, you see here more counts on the CCD camera. So what does the pump pulse do? Well, it's blowing away the neon atom such that you have more transmission of the probe pulse. But if you scan the probe pulse over that, and if the probe comes first, so over here, then you see less counts on the CCD camera, so you have a higher attenuation. So that is how you can understand here this edge that is happening here. So this is basically also a measure of the average pulse duration of the FEL. But this is not the coolest thing that we see here. What we can see if we now calculate the optical density, basically dividing by the incoming probe pulse spectrum. So here you see also, I forgot that I put this here. The gas cell is the small glass nozzle that is pushing out high pressure gas, where just above that we focus the intense FEL, and you see here the plasma recombination lines again. But if we take here the optical density of the probe, now high optical density means less counts on the camera, so high absorbance here on the top when the probe comes first, and more transparency, less absorption when the pump comes first and ionizes the target. But what I want to draw your attention on here is that in this 49.5 below energy volt range, electron volt range, we see distinct resonances appearing. And even exactly in time zero, we see another effect. There is, it's not just an outlier, there's really a very high induced transparency and transmission window here right at time zero. And we want to understand this now a bit better. So if we come with intense pump pulses at 50 electron volt to a neon atom, the easiest thing that can happen is that you sequentially absorb multiple photons. You have many photons from the FEL. So you can absorb 1, 2 photons from in the neon atom, which leads you in the end to the neon 2 plus ground state, which has a spin orbit splitting. So you have different J equals 0, 1, 2 configurations here. And from here, by absorbing another photon, you don't reach the neon 3 plus continuum, but you can from here excite these P resonances into the D shell. So from 2P on electron excited to 3D. And these resonances happen to lie exactly at this electron volt 49.4 electron volt range. And these we have identified that we observe them. And not only do we observe them, what we see in the experiment now again, increasing the XUV intensity by means of an attenuator, basically at the beginning of the flash facility. We see these resonances now not to change their symmetry, but they really shift now in their position. So this is really a direct observation of these resonance shifts and AC-Stark effect of these different resonances that we look at here. And this is enabled also because the excited state here can further be ionized. So we make these resonances kind of short-lived, which is why they appear here with a relatively broadened spectrum. And we can see also the strong coupling effect between these resonances, again, AC-Stark shift with intense XUV fields to shift them around in energy. And looking at these resonances now as a function of the time delay, we see here this additional enhanced transparency effect. And this is what I pointed to at the earlier data set. And this is now really reproduced. And we could reproduce this with few level model simulation, treating the strong coupling of these resonances, and in addition have an enhanced plasma diffraction effect. Basically, when the SASA spectra are exactly overlapping, then you have, because they share the temporal structure in each pulse, you have a higher intensity locally. And this higher intensity leads to further ionization. So you have basically a more abundant mixture and gas, a mixture of the neon 2 plus in this plasma target. And because it's a spatial volume, there can be some diffraction happening of the probe, of the pump pulse into the direction of the probe light. And by taking the measured spectra into account, we could, by using this effect, also explain this enhanced transparency window here. So that's the story on the neon atom. This neon is actually also nice to quantify and to directly time resolve the SASA pulses. So this is the latest work on the spectrotemporal characterization of these FEL pulses. Basically, we can use the transparency window that is induced here with the neon 2 plus target, which is basically transparent. So that means a time delayed probe pulse, if this has now a chirp, so on average, different colors are arriving at different times. Then in this configuration here, due to this transparency window, the greenish part of the spectrum, so the lower energy part, would be transmitted more, and the higher energy part that comes later here for a case of a down chirp, that would be more attenuated. So this is direct mapping due to this pump-induced slicing of the transparency. We can directly map the timing of the pulses onto the spectral axis. And this is what is actually encoded in the data. You see here that if you spend the photon energy and look at the absorption, we see that at the time delay point where this switches from high to low absorption, this sweeps through the spectrum. And by taking this model and invoking this model of a sliced, basically pump-induced slice of the transparency, one can directly retrieve this chirp, this average chirp, which has been realized here due to the compression in the electron punches that are responsible for the lasing. So that is technical details, of course, but the short take-home message here is that with this setup, you are again sensitive to the spectral-temporal content. So you have high time resolution and high energy resolution. So while on average the pulses might have a blurred time resolution, if you look at a single photon energy, you get a much steeper time step. All right. So and having used these pulses, now coming slowly to the end and outlook of my talk, we not only looked at atoms, so we wanted to go to more ever more complex systems. And in the introduction, I told you about the site-specific access. So we wanted to test this by looking at a rather simple molecule at first, which turned out to be really complex. This is the diodomethane molecule, and this has an atom-specific resonance at the 4D inner shell. So you can excite a 4D electron into the sigma star valence orbital. It has been orbit split, and the FEL has been centered around the 4D 5-half resonance that you see here. And this 4D 5-half resonance, we flow out here, and we scan as a function of the time delay, again, the transmission of the probe pulse, which is sharing the same energy spectrum. And we see here really a marked difference that in different energy regions, we see an increased transparency and an increased absorption for different time delays here. So this is on the 100th of femtosecond time scale. And this we could relate with the help of a very fruitful theory collaboration with Alexander Kulev's group in Heidelberg. It is known from coincidence and synchrotron measurements that this diodomethane molecule, upon XUV irradiation, undergoes a kind of a transient isomerization before it's breaking up. So basically, if you come with a high XUV photon energy, you make this one iodine molecule that are here in the purple to leave the atom. But on the way of leaving the atom, it's dissociating by forming a direct bond to the other iodine atom. And in this theory, our colleagues just set out and predicted the absorption spectra of these different geometries. And that's why this molecule is so complicated. So the absorption spectra is really a forest of different lines here that you get here from this high-level ADC3 theory. And we see here that in this geometry 1, there's more an absorption here at around the resonance at 50.5, 50.7 electron volts. So that's attributing here to the dip here, while this transient geometry 3 on the way out is having more increased absorption in the lower energy part of the region, which is more connecting here to this what we observe here. So I don't want to go into too much further detail here. You can read up the details if you're interested, of course, in the publication. But the take-home message here is that we can follow and time resolve this from a site-specific excitation and also having electron-specific, while still it's overlapping here quite a lot. It's broadened in the spectral domain, but we are still sensitive here to some molecular structural dynamics. Now we stepped it a little bit simpler, going to the oxygen molecule, where we hoped to identify really electronic resonances. And indeed, this we could do. So in the same setup, we used the FEL pump probe at 50 electron volts to look into XUV-initiated dissociation dynamics in oxygen. And here we were really happy to identify very sharp resonances that we could now isolate that are coming up at a later time. And these resonances, they could be attributed to different atomic transitions in the doubly charged oxygen atom, which can be identified here. And it's basically in an earlier related experiment that has been done in reaction microscopes, colleague in Heidelberg. Our collaborator Uwe Thum has looked at this and looking at the oxygen potential energy curves. When you come in with high photon energy, you basically open lots of different channels where the oxygen can dissociate and then finally end up in the doubly charged oxygen atom, which we can here. So that's the take-home message here. We can identify here in different transitions. And in this first preliminary experiment, which we have documented here, we just looked now at classical, letting basically a marble run down all these potential energy curves, classical provocation along the PECs, and looking at the time until it is like so far away that it can be considered an isolated atom. We see here that the time scale would be predicted on 100 femtosecond and sooner, but we see in the experiment that it's actually delayed. It's really coming up only in the couple of 100 femtosecond range. So that's calls for some delayed mechanism. Maybe it's involving some more complex non-adiabatic couplings between the potential energy curves, which of course has been ignored here. But all this, and now this is coming to the outlook, has motivated us now to propose a different experiment. So there's a beamline that is now installed at the permanent end station behind the REMI reaction microscope on the left at flash 2 with this absorption setup. And you see here that we look at these pulses here in a single shot manner with a fast detector, even being able to resolve the burst in the spectrum. So in this graph, I show you the FEL spectra for a burst of radiation. So due to the construction principles of free-electron laser, they come with 5 microsecond time space every 10 Hertz. So there's a train of 100 pulses, for instance, coming every 100 milliseconds, where these 100 pulses, they come in less than half a millisecond, sorry. And with this setup, there was this FEL pump, so high harmonic probe transabsorption spectroscopy proposal on oxygen. So besides our students, so Mark and Alexander, who have proposed this and set up this experiment, I want to highlight also Christina Papadopoulou and Elisa Appi, who have successfully operated here a high harmonic source at this free electron laser. So that is really a unique combination of combining XUV from high harmonics with FEL XUV that is coming at high intensity. And last, when was it? In October, we have done this first beam time and basically resolving in our spectrometer the high harmonic spectrum. And the idea of this experiment is that we have coupled in the high harmonics and the free electron laser also into the reaction microscope. So we were in parallel also looking at the ionized charge fragments. But here we now focus on this absorption target. And we can make use now of the flash 2 selectivity of scanning easily the FEL pump photon energy, addressing successively different potential energy curves. And with the broadband high harmonic spectrum, we can probe now much more electronic transitions that might occur here. And in this final slide, I just show you very preliminary data. So it's really ongoing data analysis, and it would be a whole different another talk that hopefully my student Alex can give also soon on what physics details we can now extract of that. So I show you this just as preliminary data that we extracted here. So here on the top left, we see the harmonic spectrum of the of different orders. So on our camera, and in this harmonic spectrum, if we switch on the FEL, you see that there's lots of resonances appearing here in the spectrum that are not there without the FEL. And the FEL stray light we see here also as a very huge peak that is saturating the camera. And if we now time delay high harmonics, so the laser that is generating the high harmonics over the FEL arrival time, we see here that we can clock the appearance of different spectroscopic lines that we can attribute to certain dissociated oxygen atoms. And it looks markedly different if we tune the FEL to, say, 20 electron volts. So that is mainly below all the potential energy curves, and also at 28 electron volts. So when we open more and more channels, we see also a lot more lines. And the ongoing data analysis is now identifying all these spectroscopic lines and also looking at their relative amplitudes and their relative timings that are happening there. So with this, I apologize a little bit for speaking a little bit over time. So really a lot of stuff that I tried to cover here. So this is basically the highlights of snapshots of what I've presented to you today. And to summarize all that, it's basically all about the nonlinear and ultra-fast control of resonant and state-specific light-matter interaction that we do both with XUV, X-ray, FEL pulses and high harmonic pulses. And in the end, it's all about controlling quantum dynamics in small atoms and molecules. And with this, I would really like to thank you for your attention.
So thank you so much for this really nice talk. Are there questions, comments? I can see them coming. Before we start, I would like to make an announcement that in 2 weeks from now, we're going to have a contributed session with early career researchers who are going to talk about hot topics. And we're looking forward to them. There's going to be 2 talks by Emil Sack and Alba de la Heras. And we are looking forward to them. And the first question from Shuai Li. Hi, I have a quick question. How do you control the delay between 2 FEL pulses for the pump probe experiment?
Yes, so yeah, that's a very good question. So that is, let me quickly jump back to the relevant slide. It's basically, so you have the FEL beam, it's a spatial beam profile. So you have a certain spatial extent. And what you basically do is you have mirrors that are going into this beam, and the FEL needs to be hit. So the XUV radiation needs to be hit under grazing incidence that you can reflect these. But now you have a mirror that is just cut at a certain point. So you're using rectangular mirrors that have an edge, and they should be polished nicely all the way to the edge. And if you now move one mirror with respect to the other, what you then do, of course, you need to have an adjacent mirrors that pick up this radiation. What you then basically do is you are increasing the optical path distance for one of these 2 beamlets, and that is exactly how you change the time delay. Making use of the speed of light, basically.
Yes, thank you. So that's also how to control the direction I mean, separate the pump and probe on the CCD. Is that correct?
Yes, yes, exactly. Actually, here on the CCD, you see the gap in between the mirrors, if you so wish. So,
Okay.
so there's, of course, there's always a little bit of light scattered because the edges are never perfect, and you have apertures that are clipping and everything. So that is why you always see some overlaps. But you can really, in the far field, you can separate them, but in the near field, in the focus, they are overlapped.
Okay, thank you.
So we have another question from Mohammed Hassan. How can you trace and control the time jittering between the two pulses from Aag and Fel in the reaction microscope?
So let me answer this question first in the direction of how we control and trace the time jittering between the two pulses. So in principle, there is a laser arrival time monitor that is basically with a cross fiber link determining when, relative to the trigger of this facility, measures the timing arrival of the laser pulses that then makes the high harmonics. And also there's a beam arrival monitor that monitors when the FEL pulse arrives on the target. Of course, you need, I mean, this is mind-blowing in my view that it's really technologically possible. Be reminded, the electrons are generated 300 meters somewhere in a building from a photocathode. They are accelerated all the way to the experiment. The laser is in a completely different building, directed over tens of meters on the experiment. And we are talking here of time precision on the order of 10 to 100 femtoseconds. So that's like on this meter, hundreds of meter scale, with the speed of light, you need to stabilize this on a micron level. So this is really amazing technologically, but it is possible with these fiber arrival links. So it's basically sending a light pulse through a stabilized fiber-based optical fiber, and then there's some cross-phase modulation done with the interaction with the laser pulses, and this feedback gives you basically the arrival time. But also here in the experiment, we basically can track the arrival time by seeing when the step is here happening. So we have basically an in situ arrival time, and while the arrival time may drift from one setting to another. So this you can see here. Here the time zero was at around 4.9 picoseconds, and here the time zero is around 4.4 picoseconds. So it has drifted. But the nice thing here is that you can compare all these different lines. They have seen the different arrival times. So we can compare the resonances relative to each other. So that is how we deal with that in the absorption spectrometer. In the reaction microscope, unfortunately, at this experiment, we have only seen the signature of the intense FEL yet. So because there's a huge intensity change, and in the reaction microscope, we cannot spatially separate the two beams. That is why the detectors have been swamped basically by ion or electron signals from the FEL and not so much from the weak high harmonics. And this is also because in this experiment, this was dedicated for absorption. So we have optimized all the parameters for this and not optimized for the reaction microscope. So this would be future to do everything with both pulses in parallel, but already with the intense FEL pulse, we can know what charge state are produced, what ions are produced. So this helps us already also a lot.
Yeah, I have no doubt. Sorry.
No, it's okay. I was about to ask if you'd like to pursue the question.
Yeah, I totally understand this for finding time zero, but I'm talking about during the time result measurement at each time instant, how you make sure your time jitter will not demolish or will not vanish your signal completely. Because if we talk about few tens of femtoseconds, few hundreds of femtoseconds, which could be the case, as I can see from this figure you are showing. So this could like sort of, ruin the time result measurement. So do you have a specific technological development to control the relative delay logged between the two pulses?
So yeah, yes, there is this technological development. These are these fiber links, and I believe, so I'm not an expert on this, but in publications from DAISY, there are possibilities to really clock and measure this by cross-phase modulation, of having basically the laser cross-phase modulated with or a fiber pulse that is then interacting with the laser in a nonlinear medium, and then sent back to the master clock. You can quantify the arrival time on the few femtosecond level, or in the order of 10 femtoseconds. And so don't quote me on the numbers here. Maybe I'm wrong. So I would direct you to the publications at DAISY. So this is possible by these fiber links. But at this very first experiment, we were kind of relying on the passive stability, also because we were averaging here over the burst. So we were measuring with 10 Hertz single shot, but in a multi-bunch mode, and we were averaging over the burst of radiation. And the timing jitter, this short pulse, the short time timing jitter, not the long time drift, but the short time timing jitter gives us also the temporal resolution here, which is on the order of 50-100 femtoseconds.
Okay, thank you.
Is that fine? We have another question from Sivarama Krishnan. Hi, Christian. In the absorption spectra, are the signatures of Raman-like processes or lines arising out of inelastic processes, especially in the excital molecules?
Hi, Shiva. Thanks for the question. In the molecules, so so to be honest, no, I don't think there are signatures of Raman-like processes. I mean, maybe you're relating also to this X-ray Raman, where you basically have a core resonance and then stimulate down to a valence excited state. It would be really cool to see that, but so far we have not been able to see that. Also, so for instance, in the diodomethane molecule, so these absorption spectra, I did not say this, these were mainly from the singly ionized molecular cation. So an absorption spectrum of the neutral molecule in an excited state would of course also overlap here. So at this point, the signal to noise ratio of the data, and given the uncertainty of many overlapping different channels that have each different theory spectra. So you can think of also different molecular geometries that have different spectra. So the quality of the data is not enough to really isolate this. But an excited neutral molecule might have a different absorption spectrum following an X-ray Raman or XUV Raman process that might appear here. Yes.
Yes, Christian, thank you. That's what I had.
I would like to ask the opportunity to thank the speaker once more for this talk, and also to thank everybody across the globe who is watching on YouTube now. Take good care of yourselves, have a wonderful weekend, and thank you for supporting our initiative, the Atto Fridays. Bye.
Thank you, everyone.